Okay, you have an image and an object. You want to like detect the type of object. Is it a cat? Is it a dog? Image of a signature, identify the writer, email, spam or not, and then you go like things become a little bit more complicated. Let's say gene expression, whether it's cancerous or not, like phylogenetic profile or tree of a gene, and then gene function, etc. These are from Peter Bartlett's slides. And then there's this last one, which is let's say if I have a text, I look at a bunch of words, right, in sequence. They call it the context and try to predict the next word, okay? So for example, here, I see, let's say, if my context has two tokens, like tokens are words, let's say, I look at gene expression, or let's say 3 tokens, gene expression is in, and I'll predict the next word, which would be a tissue, okay? And if I can do that, then I can predict the next word given the previous ones, and then I can generate text. So that's, for example, the building block of like these generative large language models like ChatGPT. So very simple idea of trying to predict the next token given the previous ones. Traditionally, this is called like supervised learning because we'll see why it's called supervised learning because we're going to get observations of both. But this is an example where like the line is blurred. Okay, so these are like trained on large amount of text and then they generate text. Okay, but you can think of the generation process as trying to predict the next word. Okay, so it's not that limited as it might appear. Okay, so very complicated state-of-the-art like machine learning systems are using some very simple at the core idea of prediction. So any questions? So far we have X and Y. Sometimes you call this features if you're a CS person. If you're like a statistician, you call it the covariate. Y is the outcome, target, response if you're a statistician. So the name doesn't matter as much. So let's start from an example. Suppose we have this table. This is from the Titanic ship that sank in the ocean about 100 years ago. And so each row is one person, whether they survive, 6, like the class, like the passenger class, the age, and so on. And these are like sometimes called tabular data. These are the data that usually statisticians work with. Here I have like showing you 10 rows out of 982. Let's say I want to predict whether someone survives. Okay, so this would be our own Y target, and then I have these other covariates or features to predict, okay? And I'm going to start with something very simple. So we're going to focus on binary classification first. That's the thing that we're going to focus on. And then I'm going to use this 6, which is another, so this is going to be our X. Okay, so X is categorical, it takes 2 values. Y is categorical, takes 2 values. Okay, it can't get simpler than that. So let's see what we can do here. So I want to like build up towards what is optimal here. So Y takes these 2 values, okay? X takes these 2 values. So statistically, that if you want to be a little bit more careful, these are going to be random variables, and you can think of each row as a realization. Okay, so we have repeated realizations of these random variables. So you can think of this as like a population level quantity. So this is a random Y, this is a random X, and there's like a joint distribution. Okay, so we assume that there's a distribution P, and the pair is drawn from this distribution P, and each row of this is a draw from this distribution. Okay, IID draws from that. That's what we're going to assume. And what I want to learn is some sort of a function that maps X to Y. So that function would map X to Y hat, which is my prediction of Y. I want this to be very close to Y, no matter like what the data point is. So as long as I'm generating from this distribution, I want to be able to predict Y based on X. So this distinction between population level or realizations is subtle. So if we can go over it, but these are abstract objects. These are realizations. So I'm gonna maybe get to it at some point, but I hope people are comfortable with this. Okay, so for your start, I'm gonna assume that we have just a pair of random variables. Okay, and then later try to connect it to this table. So far, so good. Okay, so if you want to be like very general, you're gonna not assume anything about P. Okay, so and then try to learn from data. So okay, so this distribution, the language of statistics is the population level quantity, usually not directly observed. We observe samples, so that's what I mentioned. But at first, I'm going to assume that we know P. Okay, so I'm going to give you the exact P. Let's see what is the optimal thing to do. So let me ask you. So if I have a random variable that takes these two values, and if I have another random variable that takes these two values, if I want to specify P, the joint distribution, can you tell me what should I specify? So what is like a concrete way of specifying? I want to give you P. Let's see if people are on board. So I have a random variable X. I'm going to give you a hint. So X takes values F, M, Y takes values 0, Y, 1. How do I specify the joint distribution? Like, obvious answer is also acceptable. How do you specify the joint distribution of two random variables that take each take two values? Just give it a shot. Be the first person to talk in the class. So suppose I give you one variable. How do you specify its distribution? Like I have a binary variable, X. What is the distribution of X? Can you describe that? Sorry? Go ahead. Bernoulli. Okay, so that's good. So you can say, okay, a general random variable X, you can say the distribution is Bernoulli P, but what I'm looking at, like not the name, but you just have to specify what these two values are. Okay, the probability X is like, okay, X. Let's do Y. Y takes value 0. Y takes value 1. Okay, so two numbers that would specify the distribution. Okay, the distribution is really like a probability measure that tells you like the probability of all possible events, but this is enough in our case, two numbers. And in this case, just one number is enough. Why? They have to add up to 1, so this would be like 1 minus that. So just one number, if I specify that, that's going to be enough. So now let's say I have two variables. How do you specify the joint distribution? Yes.
Probability that like F and 0.
Great. So I just have to specify the probabilities of these pairwise outcomes. Like, what is the chance that X is F and Y is 0? So that's one probability. And the other one is like the probability that X and Y is equal to M and 0, and so on, right? So there are these four numbers. Usually you put it in table called contingency table something. Okay, so if I give you four numbers and not all of the four are needed, right? How many actually do I need? Because I have to add up to 1, right? If I give you the 3, then the last one is specified. So three numbers, I give you 3 numbers, and then, but with let's say a little bit of being inaccurate, 4 numbers is enough. Okay, so I just have to give you 4 numbers. The joint distribution is completely specified. Okay, that's how you specify the joint distribution. That's what it would mean for me to give you P in this case. Okay, so once I have these 4 numbers, then I can answer a lot of questions. Okay, as I can answer, yes, a lot of questions. Is that clear? So that questions. So this is my giving you these probabilities. So suppose that these probabilities are like that. So this is giving you the joint distribution. Okay. X, Y. In practice, we don't get to see this, but you can imagine you can try to estimate this. Okay, so that's what we're going to go next. Okay. So far, so good. So what is the marginal distribution of Y, let's say? See if you understand the terminology. What is the, like if I give you this table, what is the marginal distribution of Y? This is a joint distribution has two marginals, like the distribution of Y and distribution of X. Yes, okay, so good. So the marginal distribution is giving you the distribution of Y basically. Under this joint, one of the information that I get is the distribution of Y itself, which is, if you recall, like I have to specify these two numbers, but the probability that Y is equal to 0, I just have to sum these two numbers, right? Okay, so it's going to be 62. The probability that Y is equal to 1, I just have to sum these two. And I get 38. And you can double check that this sums to 1 as well. These four also have to sum to 1. Okay, so that's the marginal distribution. In the notes, I might write something like that. Y dot is like 62, 38. You can think of the distribution as just a vector because it takes two values. Each coordinate tell you the probability of that particular. Like if the dot is here, like this thing as a vector. Okay, so far so good. Okay, so the next step is, what is the simplest classifier? So let's say I want to predict Y. The simplest classifier just ignores any covariance. Okay, I'm just going to ignore X. And the classifier always outputs a single like constant value. So if you think of the classifier as a function of X, that predicts Y hat. The functions that are constant identically. So no matter what value of X is, I'm going to always say 1, or I'm going to always say 0. So right or not so right. These are the simplest classifiers. And there's an optimal version in this case. So if I just want to ignore X, what is the optimal thing to do here? How should I predict Y?
Predict everything as 0.
Why?
Because it's more likely to be like
Great. Yeah, so it's very like intuitive because it's more likely to be 0 here. If I want to ignore every like other information, if you just ask me just to predict, I'm going to predict that someone you give me is going to die, right? That's going to be correct 60%, like 62% of the time. Okay. So the simplest classifier would be like they call it majority rule in this case. So if I want to write it, it's going to be arc. In this case, it would be like let's say argmin. Oh, actually argmin. Okay, argmax E in 0, 1. So I'm going to look at the probability that Y is equal to D, and I vary D. Set D equal to 0, set D equal to 1. Argmax means the argument that maximizes this. So this would be my classifier, the simplest classifier. I think I'm calling it. Let's see if I can see my notes. What do we call this? Okay, so let's call this MR, majority rule. Depends on X, but really doesn't depend on X. Okay, so it's going to be constant. In this case, it's going to turn out to be just 0, because the constant function 0 for X in F and M, right? So that's our simplest classifier. Sounds good. Another way of writing it is to be like, set the notation argmin, the probability that Y is not equal to D. So this is like the sort of probability of error in a sense. So minimize, because one is one minus the other, maximizing that is similar to minimizing this, because this quantity is one minus the other. Okay, so far so good. Questions? So now let's say I want to add X. Okay, so it's good to start from this. Okay, this gives you a baseline. We'll see. Okay, we'll talk about measure of performance. This is the simplest thing that you can do. If you can beat this, then good. If you can't, then you can go with this. Okay, it's always start to like good to have some benchmark. Okay, this is the simplest benchmark. So now let's say I want to use actually X to predict Y. What is a good thing to do here? What is natural? I'm losing information here. So this has more information. So I'm ignoring the X, the probability distribution collapses to this. I'm using this information. But now I want to use all the information, sort of. What do you think is? Great. Okay. Conditional probability. So instead of doing this, I can, so can we do better if we know slash use X? So the idea then is to condition on X. So that's the idea of conditioning probability. If I observe X, I condition on X, it changes the probability of everything else. Okay, so instead of computing the probability that Y is equal to 0, for example, unconditionally, I'm just now going to condition on X. Okay, let's say condition on the X being a certain value. So I want to like compute this for X being equal to F and X being equal to M. Right. So how do we calculate this? Let's say the first one. Can you like maybe walk through?
When you're on the table,
Look at the probability that Y is equal to 0, X is equal to F, right? So this is not exactly from the table. So there's like, right? So this is going to be the joint probability. I need to, not the conditional probability. There's a bit of calculation that we have to do, right? There's something else that I have to do here. Right, divide by F. So that's the definition of, so plug F here. So the probability of Y equal to 0, condition on probability X equal to F is that if you recall your basic probability, right? Probability of A condition on B is probability of A intersect B divided by probability of B. So can someone compute this? So the top would be, you can read it from the table. It's just F0 would be 0.1. This one is from the marginal of X, so we have to sum, right? So I'm going to sum these two, right? So the probability of X is equal to 0 is what? Sorry, X equal to F is 0.36, right? And the other one is 0.1. So can someone compute this? See what this turns out to be. Oh, this doesn't look good. Okay, let's do one. Actually, I just want to compute this is a little bit better. One given this is equal to, so I'm going to change this to probably y equal to 1 given x is equal to x. So that would be 0.26. Right, 0.26 divided by 0.36. So what is that? 6 divided by 0.36. Yeah, okay, so this would be 72. Right. The other one is calculated similarly, right? So can anyone tell me to like what this one would be like? Probably a y is equal to 1 given that x is equal to male or m. We 0.12, right? Divided by marginal, which is, sorry? Okay, is this correct? So 0.19, I suppose. Just make sure the numbers are right, okay, so 64. Yeah, we have to sum these two. Right, okay, so but in the end, that's the result. Okay, so 0.19, 0.72. And then I also have the probability that y is equal to 0 given x, but they really need to calculate that. No, because it's just 1 minus this. So I can just decide based on this because the other one is 1 minus this, okay? So suppose, for example, that I observe x to be female. What would be my classification in this case? What should I predict y to be? One, y? Who actually is? Go ahead, yeah.
Majority.
It's the majority, yeah. So it's like, again, the same idea, like intuitively, if I observe x to be f, the probability that they have survived is 0.72. The probability that they haven't survived is 1 minus this, which I haven't shown, right? So 28%. So it's more likely to have survived. So we're going to go with survive. If I want to just cut off the decision, it would be survive. And here, the probability of survival is like 0.19. The probability of not surviving is 1 minus this, so it's larger to not survive. So then we declare not survive. So this is a more nuanced classification rule. So this one is going to be like using x, we get this classifier, which is you can see it's if I think of it like it's going to be the probability that y is equal to 1 given that x is equal to, y equal to d given equal to x, d in 0 to 1. So if you think about what we just did, it's calculating this quantity. So what it does is you go plug in y here equal to 1 for a given x, let's say f, female. You plug in d equal 1 and d equals 0, see which one is bigger. And then that value would be the value that you use for the classifier. So in the case of, for example, f of f, what we did is argmax. So let's say m, because that's like probably that y is equal to d given x is equal to m, d in 0 to 1. This is just saying look at like which of probability of y equals 0 given x is equal to m, or probability of y equal 1 given x is equal to m is bigger, and give back that decision. Decision here is this guy. So decide 1 or decide 0, we sort of look at all possibilities, and the decision that makes this bigger, we're going to return that back. So that's the idea of arc max. Okay, so look at which value of D maximizes this quantity. Okay, so this, going from this to that, I did it a little bit quickly, but just think about it. This is just mathematical way of writing this simple rule. So you condition on X, look at the probability that Y is equal to 1, and also Y equal to 0, which I'm not showing because it's easy to do it in your head. And in each case, out of these two probabilities, which one is bigger decides the decision that you make. Okay, that's the idea. Right, this is the intuitive thing to do. And you can see the classifier in this case is more interesting because it did indeed depend on the value of X. So if X is female, we're going to predict that they survive. If X is male, we're going to predict that they not survive. Okay, more nuanced classifier, rather than predicting everyone just survives. Okay, and then you can imagine as you add more and more features, it gets more nuanced. Okay, so like more, maybe if they're female and they are in the like certain class of passengers and they had a certain age, then something happens. And if the age was below that, something else would happen, and so on. Okay, so that's how more information is gonna come in and change the thing. Okay, sounds good so far? Questions? Okay, I'm gonna pause a little bit, see if there's any questions. So, no questions? So how do we know, actually, how do I know that this is better? So like, intuitively, this should be better. But how can I show that maybe this classifier is better than this classifier? Any idea? Now I want to like evaluate the classifiers. Okay, so this is intuitive. But can I sort of prove that this is better than that? Classification accuracy. Okay, so what is classification accuracy? The proportion of correct classification. So if I want to like exactly that, but if I want to like do it at a population level, it's just the probability of correct classification. So proportion is like frequentist interpretation of probability. So if you repeat the experiment many, many times, the fraction of times that you're correct sort of approximates the probability that you're correct. So if I'm at the population level, I'm going to pick okay, so I actually added the features here. This should go there, but okay, so so this goes there. How do we measure performance? So an idea is classification or accuracy. Classification accuracy. So that's what it was. Classification accuracy, proportional, like proportion of correct classifications, let's say. So at a population level, population, this would be the probability of correct classification or classification rate. So the way that like the population version works is I'm going to pick a random x and y from P. I have my fixed classifier, and then I'm going to apply my classifier to x. That would be y hat, right? And then I decide, so what is the probability that y hat is equal to y? That would be my accuracy. The chance that y hat is equal to y, or if you want, to read this, the probability that y is equal to f of x. So assuming x is fixed, I draw a pair, apply it to x, see if matches this. So that's an event, has a probability. Okay, so this is the probability of correct classification. 1 minus it is the probability of misclassification, or misclassification rate. Okay. Usually we work with, in machine learning, usually people look at the accuracy, but I'm going to look at the misclassification rate rather than classification rate. Classification rate, which is like 1 minus classification rate, or 1 minus accuracy. So they're equivalent. So I'm going to look at the probability of incorrect classification or misclassification. Probability that y is not equal to y hat, or like probability that y is not equal to f of x. Okay. So suppose I give you a particular f, how do I actually calculate this quantity? This is sort of equivalent. Once I have this, 1 minus this would be that. Okay. But for a reason that we'll see, I'm going to look at this. So suppose I give you f majority. So let's say, suppose f is f majority, okay, majority rule. So this was identically equal to 0 for all x. So what would be the probability that y not equal to fmrx? What would this be? So this is going to be always 0. So simple. The probability that y is not equal to 0. Do what? Sorry.
The probability of misclassification or the classification?
Misclassification.
Then we would just have all the ones survive. That would be how many we missed, you know.
The ones that survive.
Yeah, because
Yes, so the probability, right, the probability that y is not equal to 0 is just the probability that y is equal to 1, right? Takes two values, and this is the probability of survival, which hopefully we have calculated somewhere. So like 0.38, right? Sum the responding rows or columns. So this is going to be 0.38. Because we are deciding 0, so the ones that survive, we make a mistake, right? So it's sort of intuitive. 38% of the time we make a mistake. So probability is 0.38. So that was easy, sort of. So suppose now, what do I call this? Okay, I think I call this F2 to be, let's call this F2. So that better classifier, suppose that F is equal to F2. So F2, if you recall, is X is equal to M. Okay, the other way around. F survives, male, not survived. So how do we proceed in this case? The probability that y not equal to f2 of x. So this is not so simple because this depends on x. So how should I calculate this? When x is equal to 0 and when x is equal to, sorry, can you say? F.
When x equal to 0.
Yes, that's this. So, but how do I calculate this? Oh, okay. So you want to do, right, go and look at all the possible cases. Is that? Okay, so you're going to go, can you say that again?
Up to values for females did not survive and males survive.
Okay, so the ones that we, okay, that's clever. So x is female, x is male. This is 1. This is 0. So when do we misclassify if x is female and it didn't survive, which has the probability. So this is going to be the probability that that XY pair is like X is female, Y did not survive, or X is what? Male and they survive, right? And so that's like the event, if you want. In the language of probability, this is the or is like union of these two events. Okay, so if this is like event A and this is event B, or means like union. Okay, and then they're disjoint, so it's like probability of A plus probability of B. So there's a bit of like intuitive but probabilistic argument going on. So these two cases are disjoint events. They can't happen together. So we make an error if this happens or this happens, which is the union. It's just the sum in this case because the intersection is 0. Like empty, the probability is 0. The probability of this is f0.1. And then the other one is, what is that? 0.12, right? Okay. So this was very clever. This is not how I intended it to be done, but this is good. There are different ways to calculate the probability. Thank you. What was your name, by the way?
Amazing.
Nancy. Okay. Great. Sounds good. Okay, so we calculated this 0.22. Any questions about this calculation? So this is where you get a little bit into probability, okay? So hopefully this argument makes sense. So this is an event. This can be written, when I said it's enough to specify the joint distribution by giving these 4 numbers, now I can like calculate the probability of any possible events involving these 2 random variables. And this is one particular event. If I specify this classifier, what is the chance that I misclassify? That's an event in terms of these 2 random variables. And if I have the joint distribution, which is enough to have these numbers, then I can calculate all these probabilities. And this is how you can do it, one way of doing it. Okay? Questions? Point 22. I'm going to stop here, see if any questions. There's point 22 and there's point 38. So which one is better? If you want to reduce your classification error, then this is better. If you want to do something else, maybe something else is better. So better is like a subjective, right? It's like depends what you mean by better. So if your goal is to minimize misclassification error, then we calculated the misclassification error or the misclassification rate. or equivalently accuracy. So the error here, the error rate or misclassification rate is higher. So this more nonce classifier is doing better, 20% of the time versus 38% of the time. Okay. So that's sort of the end of the, like almost the end of the story here. Okay, so we did a complete analysis. So you picked up 2 guesses and then you evaluated them. Okay. And then you declared that this is good. Okay. And you can see there's like a significant sort of improvement. So you reduce it by like a factor of 2, just including this covariate. So so it's not like 0.38 versus 0.37 or 0.35. Right? Sounds good? There's another way of calculating this actually. Any other idea of how to calculate this? I can do a different thing, similar to the way I constructed F2. Yes.
Given condition by x on x.
Great. Yes, that was what I intended. So use the joint approach 1. Use conditioning approach 2. Condition on x. So can you walk me? So what's your name, by the way?
Nacho. Nacho.
Nacho. Okay. Can you walk me through how to condition? So how do we condition?
Given the x, it was f plus the thing given that x was n.
Okay, so let me do this here. Equal to y not equal. Actually, I can do this. Copy, paste, the same thing, but then I'm going to change.
Multiplied by probability.
Yeah, so there's something missing, right? Probability of x is equal to f, right? And then probability that x is equal to m. This is, if you recall, this is going to be actually the joint probability. The probability that this holds and x is equal to f, right? This probability of A given B times probability of B is probability of A intersect B. So you're just breaking, it's like just basic probability, just recall. Probability of A, I want to do it, I'm going to do probability of A intersect B union B complement, which is going to be probability A intersect B union probability of A intersect B complement, which is just their disjoint plus probability of A intersect B complement. This would be probability of A given B divided by probability, times probability of B. Because the definition is the other way around. So this is this divided by that. I can write this as that. And so this would be this term. And the other one, the complement would be that, right? Just a little bit of basic probability. Well, hopefully, like once you do it a lot, this is sometimes called the law of total probability. You condition a random variable times the probability of this, and then you sum like all the possible outcomes. So now, what is? I think we can calculate this from the table, right? And we did this before, I think, somewhere here. X being f is 0.36. The other one is 0.64, right? So 0.36, I believe. 64. You're not. Yeah. So how do we calculate this piece? once I condition an f, what happens to this guy? Sorry, an x. This is now known, right? Because once I condition an x, this is going to be like f2 of f, right? So this is really probability of y not equal to f2 of f, which is in our case. And then I can actually drop this part because, oh, actually, I can't drop that. Sorry. So f2 of f is survive, right? So this is 1, right? So in this case, that's the idea. Once you condition on x, the classifier is completely determined, then I can do the conditioning. And we actually evaluated the conditioning before. So this is the probability of y is not equal to x given x is equal to f times that probability of x is equal to f. So this is how we actually determined the rule, if you remember. So I chose specifically for x is equal to f, I chose the decision such that the probability of y is equal to 1 is maximized. But in any case, so this is the probability that y is equal to 0. Y is equal to 0, and that is supposed to be 28. So this whole thing is 0.28 if we calculate, because the probability is equal to 1 is the probability that equal to 1 is 0.72. The probability is equal to 0 is it's not equal to 1 is 0.28. The other one is going to be the complement of this, right? Which is going to be 81. Oh, sorry, not 81. Our decision is, okay, that's problematic. So it's going to be 0.28. This is going to be the probability that y is not equal to, in this case, the decision is 0 times probably that x is equal to m. So this was 0.36. This is 0.64. This is the probability that y is not equal to 0, which is the probability that y is equal to 1. That's actually what I calculated above, which is like 0.19. Okay, so this was the probability that y is equal to 1 given x is equal to m. That's actually the probability of error. Because in this case, we decided with 0 because it was higher. So this is really the probability of error in this case. So there's a conditional probability of error. So that's what you get here. And then if you hopefully multiply, this turns out to be like 0.2020. And so it's not accurate because the other one is more accurate, but it's almost the same answer, right? So it has to be the same answer up to rounding errors. Okay, so this is another way of doing it. It should give you the same answer. The probability machinery sort of is consistent. Okay, sounds good. So we condition on x. Once you condition on x, you know the classifier, what classifier does, and then the problem reduces the conditional probability of y given x. Questions? So this has an advantage, this approach, which I want to discuss. To see the advantage, to see the advantage, anyone can guess what the advantage of this is? This actually tells you how to find the best classifier, right? Because if my goal is to minimize this, let's say, intuitively we did condition on x, but the question is maybe something else is better. So I have two classifiers so far. The second one is better. Maybe there's a third one that actually lowers the error more. So how do I know that? If my metric is this, I'm gonna search over all possible functions of a binary variable x, and then pick the one that minimizes this. Okay, and I mean one way of doing it is how many possible functions are actually here. So I have a function f that maps x to y. They take two values. if I want to look at all possible classifiers in this case, how many functions do I have to look at? So far, we have seen 2. How many more there are? This is a little bit math. Like you have to enumerate all the functions from M and F to 0, 1. How many possible functions? One is the constant function 0. There's an obvious one, which is the constant function 1, always declare 1. There's this guy, and then there's a flip of this, which is like 0, 1. Is there anything else? So you think about it, there's nothing else. There's just 4 functions. Okay, the space of all possible classifiers in this case is 4. Deterministic classifiers. They're like randomized classifiers, but we don't care about that. Like deterministic functions that map M and F to, it's like 2 to the 2. There are 2 options for the input, 2 options for the output is 2 to the 2. If there are like 3 here, 4 here, you can decide like it's either 3 to the 4 or 4 to the 3. I'll let you decide, figure out. Okay, it's like exponential. It's like blows up as the number of categories, but it's like 2 to the 2, the total number of functions. So one way to figure out if there's another better way is just to compute the misclassification error for all the possibilities. So we have 2. I'm going to evaluate for the other 2 and see if the other 2 do, any one of the other 2 do better. Right? Then I have the optimal classifier. Within the space of all functions, I found the function that's best. There's nothing that it's not possible to do more better. But this approach actually tells you how to find it without doing that search. Okay. The way it works is I start from this. Let's say F2 is unknown at this point. I don't know which one. It's like one of these 4. This step is true. And these probabilities are not up to me. So they're determined by the joint distribution. But these conditional probabilities are up to me. If I change F, these are going to change. And when I condition on X is equal to F, this is going to be a deterministic value. And can take either 0 or 1. And I can exactly determine which one I want by trying to minimize this. Okay, the one decision that makes this smaller is the decision that's optimal for this. So in this case, I'm going to set y not equal to 0, calculate the value, y not equal to 1, calculate the value, pick the one that's smaller. Right? The same goes here. So plug in m. For that one, set this equal to 0, set this equal to 1, pick the one that's smaller. So if you think about this, this is exactly what this rule is doing. Okay. So the one that maximizes this is equivalent to like minimizing the probability that y is not equal d. Because these are complement of each other. If you maximize this, like minimizing, it's 1 minus that. Right. So that little argument that I did there just shows that this is the optimal classifier. Okay. So by conditioning, there is this part which I can't change, and this part which is up to me. I chose the best possible. I minimize each of these terms. This can't go further than that. And so this gives you the general rule for the optimal classifier. That's the general rule in this case. And actually the same argument extends way beyond this. We'll get back to that. I'm going to talk about it next time. But this is how you drive the optimal classifier. So we proved that this classifier achieves the smallest possible error. So in this problem with these 2 variables, like x and y, you can't go beyond 0.22. No matter what you do, you can't beat this. This is like the best possible, sometimes called Bayes error rate, or like this is the optimal rate. This is the error that you pay because of the randomness in the distribution. Okay. So like if you have infinite, so we're assuming we at the population, we have infinite sample size basically, but you can't beat this. So this is sort of the end of the story for this problem as long as you have just X and Y, this is the end of the story. So how can I like improve this potentially by adding more features, let's say. Any questions? Okay, I guess we're right on time. So it's a good place to stop. Next time I'm gonna come back and like formalize these a little bit more. Okay, thank you guys. See you next time.